Hello. In this video, we're going to be exploring vertical asymptotes, and eventually we'll look at some horizontal asymptotes as well. So let's start off with a simple rational function here. We have y equals x plus 1 over x squared plus 9x plus 20, and we would like to determine the vertical asymptotes. Now, whenever we're presented with something like this, we want to look at that denominator, and this is where the vertical asymptotes are going to come from. In particular, we know that we're not allowed to divide by 0, and so vertical asymptotes would come from any 0 in the denominator. If there was anything making that bottom of the fraction 0, of course, then we would be dividing by 0, and that would be impossible. So we can't divide by 0. So let's see, how could we make the denominator 0? Well, where might that problem arise? Well, the x squared plus 9x plus 20 isn't a great form for talking about that. But if we go ahead and factor this, we can find this as x plus 4 and x plus 5, because 4 plus 5 is 9 and 4 times 5 is 20. What that means is x equals negative 4 and x equals negative 5. Those two numbers will make the denominator 0, and those will create vertical asymptotes. Now, you might have in other classes said, well, then the NPVs are x equal negative 4 and x equal to negative 5, and that's okay. You can state them like that. Here, we're going to call them vertical asymptotes. So we would say the vertical asymptotes are x equals negative 4 and x equals negative 5. Just be careful that you don't say something like this. The NPV is x not equal to negative 4, because by saying it's an NPV and then saying it's not equal to, you've kind of done a double negative there. So let's just avoid using the not equal symbol, and we'll just clearly state that we have a vertical asymptote or we have an NPV. All right, we got another one here looking for those vertical asymptotes. Well, again, we definitely want to factor this up. The current quadratic isn't really good for determining vertical asymptotes, but if we write it as x plus 2 and x plus 3, 2 times 3 is 6, 2 plus 3 is 5. Hey, that looks pretty good. But we can't just say that x equal negative 2 and x equal negative 3 are our vertical asymptotes. You know, we want to maybe just box that and be good to go, but we can't do that because we haven't fully simplified our rational function. This x plus 2, x plus 3 really should be rewritten. We should really have y equals x plus 3 over x plus 2, x plus 3. And now we see that the x plus 3 is in common with the top and the bottom, and it cancels out. So that gives us y equals 1 over x plus 2. So now, instead of saying this, we would say we just have a single vertical asymptote at x equals negative 2. And so that positive 3, it wasn't a vertical asymptote. Technically, that would be a hole. X equals negative 3 is a hole. Or another word for it would be a point of discontinuity. Point of discontinuity. Or if you're looking for an acronym, a POD. But whatever it is, it's not a vertical asymptote, because a vertical asymptote has to remain in the denominator the entire time. If it cancels out, well, you might say, oh, yeah, x not equal to negative 3. It's not a permissible value. Sure. But we now have a little more refinement. Some NPVs do indeed become vertical asymptotes, but some NPVs go on to be PODs, or holes. And we have to determine which is which based on whether the factor cancels or doesn't. It's not simply enough to be an NPV to graduate and be a vertical asymptote. You have to be an NPV, and then you have to stay in that denominator the whole time. So if you get canceled out, you lose your status as a vertical asymptote. All right, now the real question. Could we find the vertical and horizontal asymptotes? Well, this one we've been given a nice, just simple x plus 3 on the bottom, We can see that nothing cancels, and so I think we could quickly say the vertical asymptote is at x equals -3. But that horizontal asymptote, this is the first time we're asked for this. How could we find the horizontal asymptote? And the best thing to do without actually sketching the whole graph would be a little bit of simplification. We can't simplify in the sense of canceling something out, but what we can do is treat this like a division question. This is sort of like 2x plus 1 divided by x plus 3. Well, we could put the 2x and the 1 up here in a synthetic division, and the x plus 3 means you'd have x equals -3. So if I put that over here, drop down the 2, multiply -6, add down to get -5. What that means is I could rewrite my division as follows. Y equals 2 plus remainder over divisor. Now if I wrote that in a different order, I could say I have -5 over x plus 3 plus 2. And this portion here would be representing maybe like a reflection, a stretch, a vertical stretch, a translation looks like it's next to the x, so that would be a horizontal translation. But all of that's a little bit irrelevant. What I want to focus on is this plus 2. This plus 2 is going to be a vertical translation of 2 up. And so if you can imagine the original graph, right, the original y equals 1 over x graph looks like this, and it has a horizontal asymptote right here. Horizontal asymptote at y equals 0. Well, if I move that up 2, now 1, 2. Now I'm going to have a horizontal asymptote at y equals 2. And so based on that logic, I can say I have a horizontal asymptote at y equals 2. I mean, we got the answer there by using some synthetic division, but it seemed a little tricky. And we're going to look at another example where this gets a bit worse. See, we want to find the asymptotes, vertical and horizontal, but in this case we have an x squared plus 1 in the denominator, and so we can't actually use that synthetic division trick. And, well, actually I don't even know if we have a vertical asymptote here. This would have to factor, but if you tried factoring x squared plus 1, I mean, you could maybe try maybe one factor here, try another factor. Eventually, b squared minus 4ac is going to be negative. This is not factorable, so that's not good. I guess that means there's no vertical asymptote. Is there a horizontal asymptote? Yeah, it's seeming pretty tough. So what we're going to do is we're going to make a table of values and see if we can kind of draw some inferences for those asymptotes from the actual sketch. We'll just plot some points. So let's go ahead like this. We've got x. This is like y equals. Okay, so maybe we'll do -1, -2, -3. 1, 2, and 3. That's always a safe bet. So go ahead and pause the video and fill in some points. See what you come up with for your table of values. All right, hopefully you gave it a try. You should have some numbers like this. When you plug in 0, you should get 0. When you plug in 1, you should get 4 over 2, which is 2. When you plug in 2, you should get 8 over 5. When you plug in 3, 12 over 10. All right. Now let's go for the negatives. If you plug in -1, you should have -4 over 2, which will be -2. If you plug in -2, you should have -8/5 and -12/10, which is also -6/5. All right, let's go ahead and sketch these and see what we come up with. All right. So at 0 and 0, 1, 2, 2 and 8/5. Well, that looks like it's coming down a little bit. 8/5 is between 1 and 2. 3 is going to be 6/5, so pretty close to 1. Huh. Okay, well let's go on the other side. We've got -2. We've got -8/5, and we've got -6/5. Well, I mean, if I was just to connect that, that's like a pretty weird shape. It doesn't really help us find any asymptotes. In fact, it feels like it's making the problem a bit worse. But let's go ahead and pick maybe a really big value for x. We could pick maybe 10. So if you pick 10, well, you would get 4 times 10, which is 40, over 10 squared plus 1. So that's 40/101. Okay, so I guess that's going to be less than 1. Maybe that's kind of over here. Okay, let's go bigger. What if I picked 100? Well, that would be 400/100 squared plus 1. Well, I mean, some quick math will tell you 100 squared plus 1. That's going to be a pretty big denominator. 400 is not that big on the top, so I think that's going to be getting pretty close to 0. So it sort of looks like on this side, the graph is kind of doing that, which means I think we have a horizontal asymptote here at y=0. If you kind of did the same thing on the other side, you would find the graph sort of, again, swooshing in this way. So, I mean, this middle part's kind of weird, but just ignore that for right now. It looks like y=0 would be the asymptote. Let's take a look here at Desmos. All right, well, here on Desmos, we can see that, yeah, that graph, I mean, it looks a little smoother than ours, but there's the basic idea. And as we move along this way, we clearly see an asymptote at y=0. Same in the other direction, so I could go ahead and pop that on. Maybe make it a nice little dotted line. And yeah, it looks like we have a horizontal asymptote at y=0. Okay. Let's look at another one here. Let's look at another one. So this is the graph of 4x squared over x squared plus 1. So what I've done is I took the x and I went and squared it. Instead of just having a regular x, I have x squared. Now this graph looks pretty weird, but it does look like it has a horizontal asymptote. You could kind of imagine drawing something along here like this. And that would be at y=4. Okay, so I saved us a bit of work here by graphing it for us, and we can see there's an asymptote on it, but it's really weird. Now this is for some reason at 4, and the other one was at 0. This isn't making a whole lot of sense, but I'm going to show you one more picture, and I think it might help. Here what we've got is y=4x squared, and now I've changed the bottom to make it 8x. Well, now the graph looks a lot smaller, kind of shrunk down a little bit. This actually right here would be 1. And so the asymptote we would sort of draw on this graph looks like it would be at y=1/2. So that would be the horizontal asymptote. Huh. Okay. And then, well, let's just make it even more confusing. We've got 4x cubed over x squared plus 1. So here I've increased the power of x again. Now we have this graph, which, I mean, this really clearly has no horizontal asymptote. Okay, we need to bring this together because this right now isn't making a lot of sense. So let's write down what we've discovered. So we have here the y equals 4x over x squared plus 1, and that looked sort of like this. We had this sort of shape that was kind of like that, and it had a horizontal asymptote at y equals 0. Then we had the equation y equals 4x squared over x squared plus 1. That was kind of a weird valley shape, and that had the horizontal asymptote at y equals 4. Then we kind of messed with it a little bit and put an 8 on the bottom, and that suddenly shrunk the graph way down, became just a little itty bitty graph with a horizontal asymptote at y equals 1/2. Give you a little hint here. 1/2 is the same as 4 over 8. And then we went ahead and made the power even larger. And then in this case, we got a graph that didn't seem to have any horizontal asymptote. So no horizontal asymptote. Now we need to synthesize all of this because something's going on. There is some kind of pattern here that we need to be able to identify so we can figure out kind of when do graphs have horizontal asymptotes, when do they not, what's going on. Now I think the easiest one is this last one. If we look here, there's no horizontal asymptote. And the key between all of these, if you're looking, is the power of x on the top compared to the power of x on the bottom. In other words, the degree. If we were to look at the degree of each one of these rational functions, well, we would find something interesting. Here, we have degree 3, because of the x cubed, divided by degree 2. Well, which degree is higher, would you say? The degree 3 or the degree 2? Yeah, it's pretty obvious, the degree 3. So in this one, the degree on top is higher. The way I remember this is I say that this graph is top heavy. It's like the one on top, the degree on top is heavier. It's larger than the one on the bottom. And in this case, we're always going to have no horizontal asymptote because the graph is just growing too quickly in the numerator. So there's no horizontal asymptote. It just goes up and to the right or down and to the left. Now, if you look over at the first graph, well, this one had a degree of 1 on the top and a degree of 2 on the bottom. Oh, okay, so it looks like here the degree is higher on the bottom. So naturally, I refer to this graph as bottom heavy because the degree on the bottom is heavier than the degree on the top. And in this case, the horizontal asymptote was y equals 0. In fact, if you try this on Desmos, and I encourage you to pause the video and give it a try, take any rational graph, y equals, you could try 7x over x squared plus 1. You could make this even maybe 8x squared over 3x cubed plus 11. As long as the degree on the bottom is heavier than the degree on the top, you're going to end up with a horizontal asymptote of 0 every time. So these two cases are easy. Bottom heavy gives you a horizontal asymptote of y equals 0. Top heavy gives you no horizontal asymptote. But what about the case we have in the middle here? Well, it looks like the degree is the same, right? Here, we would say the degree is equal. The 2 and the 2, these are the same. So when we have something that's not top heavy, or not bottom heavy, but something that's the same, this is where the real magic happens. Because Well, if it's the same, you get an interesting asymptote. Here we had an asymptote of 4. Here we had an asymptote of 1/2. I think you can probably see the answer, but in case you're still a little bit curious, maybe it still looks a little bit mysterious to you, we take the 4 and we take the 1, those leading coefficients, and we simply divide them. 4 divided by 1 equals 4, and there's our horizontal asymptote. 4 divided by 8 equals 1/2, and there's our horizontal asymptote. Now I would encourage you to try this out with a graph on Desmos. This is one of those patterns that's best seen rather than told. And so I would encourage you, pause the video, take some different rational functions, play around with the numbers in the numerator and the denominator, play around with the degrees, and get comfortable with determining that, yeah, okay, if I have a bottom heavy, no matter what, the horizontal asymptote will be 0. If I have a top heavy, no matter what, there will be no horizontal asymptote. And if they're the same, sometimes I call this balanced. If they're balanced out, then you're going to get this situation where you divide the leading coefficients to determine the horizontal asymptote. Now, I know this was a lot, but it's actually a very helpful technique, and I want to show you back on that problem we did with synthetic. So if you remember, we had y equals 2x plus 1 over x plus 3. And we did this kind of fancy thing with synthetic division to determine the horizontal asymptote. But now with our new skills, I think you could determine it right away. This is degree 1, this is degree 1, so this is balanced. If it's balanced, we know the horizontal asymptote will be at y equals 2 divided by 1, which is 2. Done. Our horizontal asymptote just pops out now that we can see the pattern and we have a formula for determining horizontal asymptotes. Now, one thing you might still be wondering about as we talked about this is there was an instance where we actually crossed a horizontal asymptote, and this is just unfortunately one last thing we have to talk about before doing another example. Let's look at this graph here. So we have y equals 4x divided by x squared plus 4x minus 5. Here this graph would be bottom heavy because the degree on the bottom is 2, degree on the top is 1. So therefore we would have a horizontal asymptote at y equals 0. And we can draw that on the graph here. And we can see clearly that, yeah, if we were to extend this graph with a little arrow, we'd have a horizontal asymptote there, and the same thing on the other side. But that's not what your eye is probably drawn to. You're probably having your eye drawn to this right here, where the graph is crossing the horizontal asymptote. And it's very important that as we talked about asymptotes in class, they're not these magical lines you can't cross. They're simply guidelines for sketching your graph. And so the truth, which you may not have been maybe as clearly explained in previous years of math, but the truth is that you can cross asymptotes. It's not a big deal. Asymptotes have nothing to do with magical lines that you can or can't cross or these no-go zones. It's not a great way of conceptualizing them. Asymptotes are simply guidelines that help you sketch your function. And in particular, they help you sketch your function as you go really far to the right or really far to the left. They actually don't do a whole lot of guiding when you have small numbers near the origin. And so here with these small numbers of x, positive 1, positive 2, negative 1, negative 2, the asymptote really plays no role in the graph. And so it's more than welcome to cross right there. It's just as you extend out really far to the right that the asymptote actually does something in terms of helping you sketch the function. So just in case you were wondering, yes, you can cross asymptotes. All right, now with all that behind us, let's go ahead and do a full problem. We have a function here. We're looking for the vertical asymptotes, the horizontal asymptotes, the holes, the whole 9 yards. So go ahead and pause the video and see if you can come up with all of those pieces of information. All right, hopefully you gave it a try. What we need to do, of course, is some factoring. So we can notice that there's a 2x in the numerator. That'll give us x squared minus 4x plus 3. In the denominator, we'll notice there's a 5x. That'll give us x squared plus x minus 6. Then we'll keep working on it. So this looks like x minus 3, x minus 1. And here we have x. Looks like x plus 3 and x minus 2. So now we can go ahead and see if there's any simplification to do. Looks like we've got an x that's in common. We can cancel that out. And the rest of it looks like it's going to stay. That's okay. So canceling that out means we have a whole at x equals 0. And we can quickly determine the coordinates of that whole by plugging it in. So y equals 2 times 0 minus 3, 0 minus 1, over 5 times 0 plus 3, 0 minus 2. That's going to give us positive 6 over negative 30, or negative 1/5. So the whole is at x equals 0, or you could put the coordinates 0 and negative 1/5. Okay, the vertical asymptotes, well, the x didn't survive the canceling, but the other two did. So both of these will be vertical asymptotes. X equal negative 3 and x equal to 2. And that horizontal asymptote, well, we can kind of go back to the original version, and it's probably easiest here. We look and we see a balanced rational function. So we grab those two coefficients, the leading coefficients of 2 over 5. And so we have our whole, we have our vertical asymptote, and in fact we see now that the horizontal asymptote is probably the easiest of them all to identify. You can simply look at it and just grab it right away, no factoring required. Now, just to make sure that you trust this, we're going to go ahead and graph this on Desmos to confirm that our horizontal asymptote, vertical asymptote, and whole are indeed correct. All right, so here we look at Desmos and we can see, yes, we've got ourselves our whole at 0 and negative 1/5. We have our horizontal asymptote right there at 2/5, and we have two vertical asymptotes. Again, interestingly, it looks like the graph is going through right here. It's going through that horizontal asymptote, but that's not a big deal as long as we use it as a guide for sketching. As we go really far left or really far right, we're good to go. So let's go ahead and take some notes on this. We are finding vertical asymptotes, horizontal asymptotes, and wholes for rational functions. The basic idea here is if you have something, maybe I'll put it in factored form. If you have something like this, with maybe an x minus 2 on the top, anything that cancels out gives you a whole. Anything that's left over gives you a vertical asymptote. And you can either use your original version or your simplified version. And from here, you can determine the horizontal asymptote based on whether it's bottom heavy. So in this case, you'd have the degree on the top being lower than the degree on the bottom, or if you have balanced, or if you have top heavy. So bottom heavy, balanced, or top heavy. In this case, it looks like we have bottom heavy because we have degree 1 on the bottom and we have nothing on the top. And so in that case, you get y equals 0. If it was balanced, then you get the coefficient on top divided by the coefficient on the bottom. And if it is top heavy, then you get no horizontal asymptote. And using that, we should be able to identify all of our different properties that we need for sketching these rational functions. Now, just for a nice example here, we could reverse this problem. So why don't you go ahead and create a function? So your goal here will be to create a function. So in other words, like a y equals. And I want it to have the following properties. Make it have a horizontal asymptote at y equals 0. Make it have a vertical asymptote at maybe x equal to 3. And give it a POD at maybe x equal to 5. So go ahead and come up with a function that meets that criteria. And then of course down here, you can try one. We're working here on worksheet 8. And then any things to remember. Hopefully you enjoyed this video. And as always, thanks for watching.